Molecules can either be the same, so identical to each other, or different, but there are a number of ways they can be different from each other. There are some questions to ask of the molecules to discern in what way they're different. The first question is, do the molecules have the same formula? If no, they're not isomers. But if the answer is yes, the molecules are isomers of each other. That's to say, they have the same atoms. Now, where there are isomers, the next question is, do molecules have the same connectivity? That's to say, the same atoms connected in the same manner. If the answer is no, then they are constitutional isomers. Thus, the same group of atoms are bonded together, but with different bonds to different individual atoms, as we see with tetrahydropyran on the left and cyclopentanol on the right. However, if the answer is yes, we are dealing with stereoisomers where the same individual atoms are connected to the same other atoms via the same bonds. The only difference between the molecules is the spatial location of parts of the molecule. With stereoisomers, we need to ask, can the molecule be interconverted by the rotation of a single bond? Where the answer is no, we're dealing with configurational isomers, where to interconvert between the isomers, bonds must be broken and formed. More on that in a minute. If the answer is yes, we're looking at conformational isomers. Okay, back to configurational isomers. We need to determine if the isomerization is due to rotational restriction. If it's not, then we're looking at optical isomers that we will discuss more about shortly. But if the answer is yes, we are looking at geometric isomers. A great example of this is found with certain patterns of atoms attached to a double bond. They're given the descriptors of E and Z. But that's not the only circumstance where there is a restricted rotation. These isomers can also be described using an older descriptor methodology of cis and trans. Thus, sometimes they're called cis-trans isomers. In an organic context, you must have a restricted bond rotation. First, we identify the bond of restricted rotation. In the case of the double bond, well, it's the double bond. On the left of the bond of the restricted rotation are two different groups. Here it's generic A and B. On the right of the bond of restricted rotation are another two different groups. Here we're calling them C and D. The difference between the isomers is where one set of groups, here it's the left set, stay the same, and the other set, here it's the right set, for example C and D, are in opposite locations. This is not just restricted to double bonds of restricted rotation. We also see it in rings of an appropriate size where bond rotation is again restricted. For example, here with this cyclohexane, you can spot the same four generic groups as we saw in the double bond case. And again, the difference between the two isomers is that the right groups, C and D, swap places, whilst the left groups, A and B, stay in the same location. It doesn't matter if it's this situation or if it's the left group swapping places and the right group staying in the same location. These geometric isomers have different physical properties. So, for example, different melting points or different boiling points. With inorganic chemistry, things are slightly different. This is an organic course, so we're not going to dwell too much on the inorganic chemistry, but I want you to be aware that it's there. There's no bond of restricted rotation, but there are four groups here. Due to the molecular orientation, there's a top set, Cl and NH3, and a bottom set, Cl, and NH3. The bottom set stay the same, but the top set switch places between cis and trans. This cis molecule is actually called cisplatin, and it's a drug to treat cancer. Inorganic cis-trans isomers are found in octahedral and square planar coordination complexes. Diastereomers have more than one stereogenic center and are non-superimposable, but they are not mirror images of each other. These isomers have a relationship of relative stereochemistry. Stereogenic centers are a point, very often an atom, where two attached groups can be interchanged to obtain a stereoisomer. So relative stereochemistry is how one stereogenic center compares to another, where two substituents, one on each stereogenic center, can have a different spatial relationship with each other. Diastereomers have different physical properties, such as melting point and boiling point. On the other hand, enantiomers have one or more stereogenic centers, with non-superimposable mirror images, and thus no plane of symmetry. There's an absolute stereochemical relationship between the isomers. They have the same spatial relationship between two substituents. Enantiomers are not physically different from each other, except for the rotation of plane polarized light. Now, enantiomers have no plane of symmetry. But what would happen if a molecule has internal plane of symmetry? This is achiral, and the mirror images are superimposable as a result. With this example, the plane of symmetry is not immediately obvious, but if we rotate the central bond by 180 degrees, the plane of symmetry becomes clear. Thus, the mirror image of this generic molecule is identical. This single molecule with more than one stereogenic center is described as mesoachiral.